So here we go. So let's finish up moments here today, shall we? If I can, having some more computer problems here, but so what else is new? But there we go. So what we were doing here last time is we were looking a little bit at cross products, if I remember right. Okay, so this is another vector operation. And this is one of those things that our friends and mathematicians came up with. It's very helpful for us. So what we want to do here is cross two vectors. And I know that some of you are getting this in 254, and you might be getting it in physics also. I'm not sure, but some of you aren't taking 254, and that's all fine. You just have to remember the formula for doing a cross product. So you get a vector when you do a cross product. You get a term that has a magnitude of the magnitude of the first vector times the magnitude of the second vector times the sine of the angle in between the vectors. Okay, so that's the magnitude. And then the vector itself is normal to the plane in which vectors A and B lie, and is determined by the right-hand rule, which way it points. Okay. And then we went through what happens when you cross unit vectors together. When you cross like unit vectors together, the angle between them is 0, and the sine of 0 is 0. Okay? So what happens is when you cross like unit vectors together, everything goes to 0. When you cross unlike unit vectors together, you have a 90-degree angle between them. Sine of 90 is 1. A and B are the two unit vectors that you're crossing together. Everything here has a magnitude of 1. So what you get is, when you cross unlike unit vectors, is you get a third unit vector that is normal to the plane made up by the other two, pointing in the direction as determined by the right-hand rule. So if you cross I and J, you would get a vector of magnitude 1, which is normal to the plane of I and J, which is the xy plane. So that's a unit vector in the z direction, which is k. If you point your fingers in the x direction and curl them towards the y of your right hand, your thumb will point up in the positive k direction. So I cross with J is k. Okay. Similarly, if you cross I with k, you're going to get the third unit vector. You're going to get a j unit vector, because that's normal to the plane made up by I and k. But when you take your fingers and point them in the x direction and curl them towards the z, if you use your right hand, your thumb will point in the negative y direction. So that's negative j. Okay. And you can go through and use that reasoning to determine all of these cross products. Okay. So the gist of this is, when you do a cross product, what you end up with is that rather long formula that I've outlined in black. So A cross B is AYBZ minus AZBYI. Then importantly, a negative AXBZ minus AZBXJ. Then another positive AXBY minus AYBXK. So that's how you take a cross product. And as I've mentioned, if you were to need that formula, it's right on the formula sheet. If you need it, it's on the left-hand column near the bottom. Okay, or right at the bottom, actually.
And when you do a cross product, you find the torque. You take the displacement first or the force first?
Displacement first. It's R crossed with F, and it has to be that. And that formula is shown right up above, so M equals R cross F. Now you could also do this with determinants, which is how I learned to do it. I think you, here at LB, I think they kind of teach it by taking the first two columns and putting them off to the right and doing kind of a diagonal pattern with lines to figure out what to multiply with what. However the heck you do it is fine. As long as you get to that formula down at the bottom, it doesn't really matter how you generate that. But keep in mind that you are given the formula if you need it. It's right there. Okay. Now what this will do for us, if we input the proper stuff, is that will kick us out a moment. All right? So I've got two vectors there, A and B, and I just did an example there of how to do a cross product. So if A is 3 minus 4 plus 6 and B is negative 5, 2, 7, we can do the cross. All right, and we'll get that term right there. You just plug the numbers in, and you can get the cross product, which turns out to be negative 40i minus 51j minus 14k. Now, the way I learned to do these, it's not as though you have to do it this way, but this is how I learned a long time ago, was I would cross off the first row and the first column, and then cross what's left to get the I. So I'd take negative 4 times 7. I'm using these terms right in there. So negative 4 times 7, going down that diagonal. Then I'd subtract off the other diagonal, minus 6 times 2, and that would be the I. And then I would do the J next, so I'd cross off the J column in the top row, and I'd be left with 3 times 7 minus 6 times a negative 5, and also I'd have to remember there was a negative out in front of that. That's the J. And then the K, what I would do is I would take the last column and the top row and cross that. So I would take 3 times 2 minus a negative 4 times negative 5, and that would be the K. So that's how I learned how to do it. And I had a very scary calculus teacher, so I will never do it a different way in case he gets mad at me or something. So that's how I learned. So I still do it that way, and I'll keep doing it that way probably. But again, you can do it whatever way suits you. Okay, we good with that? Okay. Now that's all well and good. You know, we enjoy learning about mathematics, but let's use it for something that we'd like to do as engineers, and what we'd like to do would be to calculate a moment. So what we do is to get a moment about A, we cross a position vector from A to any point on the force with a force vector. So M sub A is R crossed F. Notice those are all bolded there. Bolding when you're typing means they're vectors, okay? So a cross product is a vector. Now it's got to be in that order. It's got to be R crossed with F. So you cannot do F cross R. It gets you a negative answer. So you got to go R crossed F. All right? So there you go. So if you're going to cross R and F together to get the moment, you're going to get RYFZ minus RZFYI minus RXFC minus RZFXJ plus RXFY minus RYFXK. And that's how you'll generate a 3D moment. So what you need then to do a 3D moment here, rather than doing all that visualization that we did over the last couple days, is just find a vector from the point about which you're taking moments to the force. Any vector will do. And then you do a cross product of that and the force vector. Do the cross and you'll come up with the moment vector. Okay? And that's about it. Now I'm sure that you're all asking, why does that work? You know, why can't I just do a cross product and get a moment vector? So that's a very good question. I'm glad that you asked that. So let's have a look here at why that happens. Okay. Now, what we're doing, we're using any vector from A to the force. So there's any vector from A to the force, and there's the force vector. And we cross them, and that's how we get the moment. Now, the magnitude of that cross product is the magnitude of the first vector times the magnitude of the second vector times the sine of the angle between the vectors, all right? So what do we got here? We've got the magnitude of the first, which would be F, times the magnitude of the second, which would be R, But if you remember, what we want for a moment is a perpendicular distance, not just any distance, but it's got to be a perpendicular distance. So if we take the angle between the vectors, which is theta, and take r sine theta, what we get is this perpendicular distance d. So the r sine theta resolves to d, which is the perpendicular distance. You multiply that by the force. Okay? So it just happens to work out that that will generate a moment for us. We take that any old vector from a to the force vector, r, but then we multiply it by sine theta. That's embedded right in the cross product definition. And that gives us the perpendicular d that we want. And multiply that by the force and we're good, okay? And then by definition, the moment vector is normal to the plane in which the moment occurs, just like the cross product vector is normal to the plane in which the two vectors lie. Same thing. So it works out just right, okay? So there you go. So we good with that? Good to go? So if you take r cross f, you'll get a 3D moment vector is what you get out of that. Keep in mind that a moment vector is normal to the plane in which the moment occurs. Think of the moment as being a wheel. Think of the moment vector as the axle of the wheel. Okay? That's what a moment vector defines. So if I'm taking this lid off of this jar, everybody just think about this for a minute. Where would that moment vector go if I'm doing that? Everybody just think about it for a second so we all engage our brains and think about this stuff as we like to do. Okay, I'm twisting the lid off the jar, it looks like there.
Moment vector should point straight out from the center of the board.
Yeah, if you were to take like a thumbtack and tape it to the lid, the pointy part of the thumbtack would point in the direction of the moment vector. It'd be normal to the lid. It'd go off that way.
That'd be a very bad idea.
Yeah, I probably would, but we could do it temporarily to figure out our moment vectors. There's probably other ways we could do it, but what we're doing there, we're twisting that counterclockwise off the jar. The vector then is normal to the plane of the lid, okay? That's how this stuff works, okay? So keep in mind when you're just generating these vectors, that's what you're getting. We okay with that? Good to go? Yeah, question?
What is so we find the moment vector, what is the magnitude of that moment vector?
The magnitude of the moment vector is whatever the magnitude of the force is that's being applied times the perpendicular distance from the center of the lid to the force.
Right.
Yeah. And the cross product just automatically kicks that out for us if we need it. Okay. All right. So let's do this same problem we did visually, but let's do it with vectors. It's a bit more straightforward to do, all right? If we do it with vectors, so I would recommend, rather than doing it visually and figuring out all the twists and spins, I just do it with crosses. It's just easier, okay? Less potential for error. So we're just moving on to the next page, which is 810. 310. Thank you. So it's 310. And it starts like what we did before. I mean, we've done this one already visually. Let's do it with vectors now. Just like before, we want to start by getting a force vector. So you take RC minus RB, find the magnitude, which is 0.831, divide through by that, you get the unit vector, scale that up by the 600 Newton magnitude, and you get the force vector from B to C. So negative 289, negative 506, and 144. Okay. Now the next thing you need is a vector that goes from A to anywhere on the line of action of the force BC, okay? So if I were doing this, I'd take the easiest one I could get, which would be from A to C, because that's a nice simple vector. What is that, just minus 0.4i? I mean, that's it, right? No J, no K. So I would just go ahead and use that vector from A to C and use that in my cross product. So you can use any vector you want. You could use that one, you could use A to B, or any other vector you could find. It doesn't matter, just like when you're doing it visually.
It would be a huge pain to use any of them except to A to C or A to B, because.
Yeah, you'd have to figure out where they were. Well, you could probably find that one in the middle, it'd just be the midpoint, that wouldn't be too bad. But yeah, just keep it simple. Yeah. Okay. So what you do then is you just cross that vector with the force, okay? And you use that formula there. So to find A, put FBC anywhere on the line BC and calculate R cross with FBC. And there's the cross product formula. So I just used -4, 0, 0. That's all I did. That's the position vector from A to C. If I needed to find that mathematically, I'd take RC minus RA. So that's -0.400. Then I just cross that with the force. All right, now, again, I mean, you've got the formula, so don't, just plug into the formula if you have any, challenges getting that figured out. Again, I just use that crossing out method, but whatever you do is fine. It doesn't really matter. So there's cross off the top row in the first column, cross what's left. That's 0 minus 0. And when I multiply those diagonals together, that's the I component. Always subtract off the J component. Okay, and that will be cross out the column, or excuse me, always subtract the J. I should have said always subtract the J component of the moment, or term of the moment might be the way to say. Cross off the middle column, top row, -0.4 times 144 minus 0. Okay, and then the last one for the K, cross off the last column, top row, and that's positive -0.4 times -506. So what we're doing here, we're multiplying those two together and then minus 0. That's the K. Combine everything together, we get M sub A, 0I plus 57.8J plus 202K. So we're getting the same answer as we got before, just using a cross product. And what this thing does, it just combines the things we combine visually together automatically. It just takes that whole visualization process and automates it, is what it does. So rather than having to visualize, you just do a cross product, you get the exact same terms, you get the exact same answer. Okay, so we good with that?
On a test, do we have to do visually, or can we just do cross?
No, I'll just tell you to find the moment. Do it whatever way suits you.
Okay.
Just show your work, do like usual. Yeah. But yeah, I won't specify a certain method. Just do a cross. Okay, so that's how that goes. You too can do cross products. So why don't you do it? Get the cross for if the force is at B. So that's down at the bottom of the page or over on the right-hand side. So just for practice, so I want you to knock one out there. just a regular, it's right, no unit, no. The vector you're getting, when you do it, when you do the cross, is normal to the plane, is normal to curves. So if that were like a rocket or something that's just spinning about, okay, that is normal to that plane. So it's not straight, it's not the same vector. It's normal to the plane, it's normal to curves. Yeah, right, and yeah. So that point.
Yeah, well, I'm simplifying now, but.
So no unit vector here for that R, it's just a regular position vector. The reason is you want the length of the vector in there, because the bigger that length is, the bigger the moment, okay? So don't unitize the position vector here, it's just a R, it's just a position vector. You okay with that? And you should be getting to the same answer. And it should be the exact same thing we did when we did that second run at the visualization. It's the same thing, and that's something to keep in mind. This cross-product stuff, you're just automating what you would visualize. It does the exact same thing you would do if you did it visually. It just generates it for you automatically.
You have another force, and you did it this way, we just add them together.
Yeah, moments are additive, just like any sort of vector. So yeah, if you got two forces, just calculate two moment vectors and add them up. They'll come right out, yeah. Okay, so the position vector, I think is 0, battery running low, okay. 0, whatever I got up there. All sorts of computer problems here today. I think it's 0.7, -0.2, I think.
Yeah. Yeah.
And you just cross it with the force vector, and that's about it. Just be sure you can do that stuff. The important things on this are the position vector is from A, that's where you're taking the moment about, to the force. So you start at the point you're taking moments about, and from there go to the force. Okay? And then the other thing is it's a regular position vector. The length of it matters and should stay in the term, because the longer that moment arm is, the bigger the moment. So you want to keep the length of that vector in there. So you do not unitize R. You just leave it as R. Okay. And then you just do the cross product, and you can do that however the heck you learned it. As long as you get to the, you do it in a reasonable way and get to the right answer, we're good.
Running through point A?
The moment vector is attached to point A, and it's normal to the plane in which the two forces lie, or the two vectors lie, R and F.
And another question is, can you, when you're taking cross product, is it necessary for them to always have a common point?
No, they don't. And see, yeah, so that if you're doing a cross product, the two vectors don't need to have a, well, they gotta make up a plane. Hang on. Yeah, I think they do, because they gotta make up a plane, which means there's 3 points that defines the plane, and that means they gotta share a point somewhere. And that shared point is the position vector, in our case, from A to the force BC, which is point B for us this time through. So yeah, they have to share, they have to intersect at a point in order to create a plane. So yeah, they do. Okay. Okay, is that good? And so, okay, I've got the MA calculation there. There's a little bit of rounding error where it looks like it's negative 0.4i, but that's just rounding, so I just took that to 0. Okay. So any questions on that? We're good? Okay. All right. So that's how we get the moment about a point. Okay, and so when I'm doing a moment about a point, there's different ways to think about this. One way I think about it is the force is like a rocket that's orbiting around a planet, and the planet is the point about which I'm taking moments, okay? And then, so that's how this moment occurs, all right? So, and these are kind of tough for me to just draw on the fly, but basically what's happening here is I've got this moment doing that is basically what's going on. It's kind of like that force is traveling along and it's been tethered to A somehow, so it's going to start rotating about A. All right, and that's the moment. So the moment vector then is normal to that plane. So the moment vector will be kind of up this way, normal to that plane right there, okay? Y'all okay with that? That's how a moment vector is defined. It's normal to the plane in which the moment occurs. Okay. So that's what I call a free moment. If that force could create any old moment about A it wanted to, that's the moment it would create with that moment vector there. All right. So are we good with that? Questions?
So normal vector is that it's normal to the plane that it occurs.
Right, right. Defined by the right-hand rule. Yeah. Okay.
If the vector was going in the opposite direction.
Which vector? I'm sorry.
The moment vector.
Yeah.
So
If,
opposite direction, would that rotate the other way?
yes. So if the moment vector were pointing instead of up, if it were pointing down, that would basically infer that the force is going that way, and that the net moment is rotating the other direction, which would, if you rotate your hand in that other direction, you're going to get a vector that goes down that way. So if the force, or as I'm showing right there, the moment, would be coming around the opposite direction. That's what it would be doing. And so that's why your moment vector would point the other direction. So if the force were going this way, the rotation would be like that. And if I turn my right fingers that way, my thumb points down into the left. Okay. Okay. Good with that? Good. All right. So that's all well and good. And so I call that, it's just my term, I'll call that a free moment sometimes, because it's just rotating any way it wants, and I'm finding the moment if it were to do that. But I'm sure you're saying, well, wait, what? Don't a lot of moments, aren't they forced to occur about a given axis? Okay. And you're right, a lot of moments are forced to occur about a given axis. So that was a good question. I'm glad you asked that. Okay. So there we go. So if I have two hinges there, and then I've got this prop pushing up on the hood there, see, I'm forcing that moment to occur about the hinges, aren't I? Y'all okay with that?
And that just means some. means that it's only going to rotate that way, it's not going to tear off the hinges.
Yeah, right, it's this thing, yeah, this prop isn't gonna go tearing through hinges, so we're kind of forcing the moment to occur about a given line. Or I might be, or another situation might be, I might be interested in what the moment is about a given line. So for instance here, you know, if I'm having some problems here, there we go. If I'm designing, you know, this bucket here, you know, I'm going to be thinking about this. Okay, if, you know, and this is a normal thing for one of these pieces of equipment to do, pick up a big old chunk of concrete and start moving it around. That creates a dynamic moment. I might be worried about the moment about this axis. Maybe I want to go to this website, but I don't think I do, but I'm having problems here. There we go. Be very careful here. So you're supposed to have small, delicate hands to do this stuff on this little laptop, and I just don't have that. I'm not a lead guitar player, I'm a bass player, you know, I can't do those little quick notes, it just doesn't work. I tried to play mandolin once, and that was kind of a joke, you know, it just didn't work. Can't do lab work, I'm a total disaster in a lab, it's just not good. But anyway, here we go. So I might want a moment there, and what's going on there? Why might I care about that moment, about that particular axis along the tracks there? It might tip over, yeah, okay. So I might want to look at that. So now, I just don't want the moment about a point now, I want the moment about an axis, okay? So that's something we could look at. Now, if we think a little bit about what a moment vector is, if we just look at that free moment there that we had, there we go. So if we look at that free moment right there, which was the top one, what if we force that to occur about some axis? Okay, if we do that, what we're going to do is get back on the stuff we did with projections. If we find the moment, instead of that, allowing that to be a free moment, if we force it to occur about a given axis, what we would want to do then would be to take that red moment vector that points up and to the right and project it down onto whatever axis we're using. Okay, like that, and find the component of that vector that acts normal, or excuse me, along the axis. So I've got this kind of messed up right now. I think I've got a better sketch of this, so why don't I just go there. Okay, so the next page of your notes, which I think would be 320, let's see if we can find the moment of that vector about this axis here. So now I'm going to put in a couple of bearings there at A and at D. And I'm going to find the moment of that force about that particular axis. So I'm going to force it to rotate about those two bearings at A and D. Okay? So I'm finding the moment about axis AB. So what I'm doing here is I have this moment vector about A, which, you know, we've looked at a number of times here. It's doing something like that. But then I'm going to make that rotate about an axis AD. So if I make it rotate about axis AD, what I'm after here is the component of that moment that acts along the axis, because the axle about which a moment occurs is the line of the moment vector. So I'm going to take that red moment vector going up and to the right and force it and project it down into the axis and find the amount of it that occurs about that axis AD. So what I'm going to want to do is project that thing down onto that axis. And I'll do that with a dot product again. Okay? So if you're in this particular situation when you want to find a 3D moment about an axis, this is how you do it, okay? All right, so I'm going to start off the same sort of way that I have before. I'm going to get that force broken into a vector. So I make a force vector out of it. This is like the third time we've done that, okay? It's the same force vector, so same process. So then I get the force vector, and then I'll do a cross product. So I'll cross it with a vector from A to C. That's the simplest one to use. And I'll do the cross, and I'll come up with that moment. 0I plus 57.8J plus 202.3K. Then what I'll do is I'll dot that moment vector, which, as I mentioned, is going up this way. I'm going to dot it with a unit vector that represents the line of the axis that I'm forcing the moment to occur about, which is right down there. So I'm going to find this component of that moment vector, because a moment vector acts along the axis that the moment rotates about, okay? So I'll just do a dot product is all I got to do here, okay? So there you go. So I'll just find a unit vector from A to D, and then I'll do a dot product. That's about it. Okay, so I'll find a position vector from A to D. That's RD minus RA. That's negative 0.4.70. I'll take the square root of sum of the squares and get 0.806, and I'll divide that through and get a unit vector from A to D. Right there. And then once I've got that, I'll just dot it with the moment vector. And this will get me a magnitude. So remember that a dot product gets you a magnitude. So that's 50.2 Newton meters. And then if I need to make that into a moment vector, a moment about an axis vector, I'll just take the magnitude, the 50.2, and I'll multiply it through the unit vector from A to D. And I'll get a moment vector about AD. Okay. So that's the process to find a 3D moment about a particular axis, which can come up. Certainly if you're a mechanical engineer, you got lots of shafts that rotate. That's what's going on there. You're forcing whatever that moment is to occur about the axis of the shaft. Okay? So, crankshafts and camshafts and any sort of power takeoffs, any of that stuff, you're getting an axis that's rotating. Okay. All right, so find the moment vector first about a point on the object and then dot it with the unit vector for the axis. Got any questions on that? Okay.
You said moment vector dot with unit vector?
Right, with the unit vector along the axis. And I think if you look at the notes there, that little written paragraph on the upper right kind of just basically describes what you need to do. And then the rest of it is just the calcs to actually do what that paragraph describes. Okay.
And if we know the axis, it's okay to answer just the scalar torque, we don't need.
Yeah, it depends. I mean, quite often you just need a scalar, because what that is the torque around that axis. It's what's happening, what the moment is about the axis, right? So, the first thing you get is a scalar. But if you need the vector, it's easy enough because you already got a unit vector for the axis anyway. So just multiply through by the magnitude, and you'll get a vector if you need it. Okay. Okay, so why don't I get you some of these to do for Wednesday? It's supposed to be nicer this weekend, I think, so that would be good. Okay, so here's what I'd like you to do. I'd like you to do 201, and then 202, and then 211, and I've got some notes on this. For 202, you're supposed to use two position vectors, so you're supposed to do it twice. For 202, AB and AC. And then 211, you can use your, I think it's an MA vector, isn't it? Yep. Use your MA answer from 201 to solve, okay? So 201 is like these examples we've been doing here today, or, you know, the moment about a point stuff, that's 201, and then 211 is a moment about an axis. So just take your answer from 201 and use it to do 211. Okay? You don't have to redo the whole thing, just use your answer from 201.
And
Yeah.
you mentioned that's a method that you have been known to use, where you use an answer for the test, that is, where you use an answer and you,
Well,
as far as mechanics, right?
yeah, I might do that sometimes, yeah. So just, you know, just keep your eyes open for that so you're not working too hard. I mean, you know, yeah, sure thing. And also, you know, if you bust the first one, I'll just take your answer that you got and independently grade the second one based on the answer you got. Yeah. question?
And you also have the 3D flow chart.
So what now? Oh, yeah. That's just, I don't know, once that came up, so I think of that stuff as being process oriented, 3D stuff. That's 325. It just has how you do different 3D operations step by step by step. It's an attempt at doing that. I don't know how effective it is, but for whatever it's worth, it's on 325. Yeah.
On the exam, can we just only use the cross product method to solve the vectors? Or
Yeah.
is it for us to know?
Yeah, so the question is about on an exam. If I give you, I'm sure I will give you a moment problem on the exam, so I'm quite sure I will, so I'll start with that. And I won't say do it this way or that way, I'll just say what's the moment? And you solve it, whatever way suits you. And just show your work, you know, usual stuff. So let's see if I can get out of here. All right. Here.